G'day chemistry students. In this video, again, we're going to be looking at dot points 5.2.1, 2, and 3. Our topic for today is Le Chatelier's principle, and what we'll be looking at in particular is how Le Chatelier's principle can explain how equilibrium systems will change when there are temperature changes. Let's get into it. So already what we've looked at with changing temperatures in equilibrium systems is that a system that has been changed in some way, shape, or form, that system that's in equilibrium will shift to counterbalance that change. So when we change temperatures, what will happen is that the exothermic or endothermic reaction will be favored to try and balance out that temperature change. Our first example here is that if we were to decrease the temperature of a system, so that would be through some sort of cooling action, that the exothermic process would be favored. In other words, if we drop the temperature, the exothermic process will be favored because it will try to bring that system back to thermal equilibrium. In the example that's up the top here, the exothermic process is the forward reaction, AB forming CD. Here, what we see is that delta H for that forward process is negative, meaning that that is exothermic heat is being released. So what we would observe is a right shift, a shift to the right that would decrease the concentration of A and B and increase the concentration of C and D. Opposite to that, if we were to increase the temperature by heating the system, the endothermic process would be favored. That means a left shift that would increase the concentration of AB and decrease the concentration of CD. Now, this is something that we looked at a couple of videos ago when we were looking just generally at how Le Chatelier's principle was affected by temperature. However, what we're going to start doing now is looking at how collision theory can actually explain that relationship that is outlined in Le Chatelier's principle. So what we need to do first is maybe have a look at our energy profile diagrams that we have looked at in previous modules. What we see here is an exothermic reaction, and then the reverse process of the same reaction, which is endothermic. So what you'll see is the peak energy requirement up the top here is exactly the same. The energy of the reactants, which are products on the other side, and products which are reactants on the other side here, they have the same energy as well. So what that means is that the enthalpy change for both of these is the same. It's just that one is positive and one is negative. But the activation energy is a little bit different for both because it's the difference in energy between the energy of the reactants, which are both here, and then the maximum or the energy required for reaction to occur. So a small jump for the exothermic process and a much larger jump for the endothermic process. What that means is if you have a system under a set of temperature conditions, more of the particles that are the reactants for the exothermic process will actually have the energy to be able to proceed forward. Versus the endothermic process where very few particles are actually going to exceed the energy of activation. Most of the particles here in this section don't have the energy to overcome the energy of activation. So what that means is when we're looking at raising or lowering the temperature, for an endothermic process, raising the temperature is actually quite a big deal. What that means is lots and lots and lots of particles now have the energy to exceed the energy of activation. That means that way more collisions are going to be successful. And if there are going to be more successful collisions, then the reaction rate of the endothermic process is going to be higher. On the flip side, lowering the temperature is going to mean that fewer reactants are actually going to be able to collide with a suitable amount of energy, drastically decreasing the reaction rate of that endothermic process. However, when we compare this to the exothermic processes, what we see is that if we reduce the temperature, lots of the exothermic reactions lots of the reactants of the exothermic process are still going to be able to proceed forwards. And for when we increase the temperature, we're not actually going to get a very large increase in the number of particles which are able to collide successfully. So what you'll usually see in an exothermic process is that the reaction rate remains reasonably steady, about the same when those temperature changes happen. Usually you'll see drastic changes to the number of particles which are able to react in the endothermic process. So usually when we're justifying why we might get a left or a right shift in an equilibrium process where there's been a temperature change, we can usually justify it by the change in reaction rate of the endothermic process. So with our classic example, if we have our nitrogen dioxide and our dinitrogen tetraoxide, and the forward process is exothermic, in the example here of a cooling system, what we would say is that there are going to be way less successful collisions for the endothermic process. So what that means is less particles are able to exceed that energy of activation, less particles are able to react. If that happens and the reaction rate of the exothermic process stays reasonably the same, then the reaction rate of the exothermic process is going to be bigger than the reaction rate of the endothermic process. What that means is that everything's no longer in equilibrium, that the reaction rates are no longer equal. So what's going to happen is the exothermic process is going to be favored, which means that there's going to be more dinitrogen tetraoxide being produced, and that will continue to happen until the reaction rates are equal. We can also graph these systems similarly to the way that we graph the adjustments of concentration of our particles when we change the concentration of one of our substances. We can sort of graph it the same way for temperature changes as well. So in this example, I've just did a little bit of an adjustment of the graph that we used last time, showing the relationship between hydrogen iodine and hydrogen iodide. In this one, what we see is that the concentrations of the iodine and the hydrogen drop, and the concentrations of the hydrogen iodide increase. And so what that means is we're looking at a situation where the forward reaction is being favored. In this case, the forward reaction is endothermic. It has a positive delta H. And what that means is that the endothermic process is opposing whatever change came to begin with. In other words, what that means is that the system was being heated up. If the system is being heated up, the endothermic process will be favored. And again, to justify that with collision theory, if we heat up the system, there are going to be more collisions of these reactants here, the hydrogen and the iodine, which are going to actually be successful, meaning that there are going to be more endothermic reactions. If there are more endothermic reactions, then the concentration of those reactants are going to drop and we're going to end up producing more of those products. Now, I think logic-wise, this kind of idea of explaining with collision theory and visualizing what some of these graphs actually mean might be a little bit more difficult than the concepts that we looked at with concentration. So we're going to spend a fair amount of time discussing some of those ideas in class to try and hash out some of those concepts. In the next video after that lesson, when we've had those discussions, we're also going to be looking at volume and pressure changes and how that can affect equilibrium as well. But until that time, have a good one.